Thank you. Thank you for the opportunity. I appreciate the opportunity to present today. As a word of introduction, as Dr. Garcia said, I'm Erik Westman. I'm a professor in mining and minerals engineering at Virginia Tech. I have a bachelor's degree in geophysical engineering from the Colorado School of Mines, a master's in civil geotechnical engineering from the University of Colorado at Denver, and a PhD is in mining engineering at Virginia Tech. Today, I'll be talking about something that I started working on, and maybe many of you are more expert at it than I, but I started on January 28th of 1991. And I remember the date clearly because it was a Monday, and I started as a new employee at the Denver Research Center for the U.S. Bureau of Mines. And that Thursday, my wife was very pregnant, and that Thursday, the fourth day of my new job, she said that the baby was coming. And I made the major mistake of saying, "Are you sure?" Because I did not want to look like I was leaving the job prematurely. But actually, the baby was on the way. We had a daughter named Anna, and she was born on the 31st of January, 1991. And so I remember the date when I started working on this problem that we'll be discussing today. And I've enjoyed working on it ever since that time. As many of you are aware, we all have other responsibilities and cannot always focus as deeply on the type of research that we really enjoy the most. We cannot focus as deeply as we would like to, but when I have time and when I'm able and I have a project, I really enjoy working on this. And so what we'll be talking about today is is understanding the
Sorry, Eric. Sorry, Eric. Can we start the recording now? Alex?
I think it
I,
is.
I, I am already recording.
Oh, sorry. Okay.
No problem. Yeah. Yeah, so the problem is that we really don't understand the behavior of a rock mass prior to a seismic event. Of course, along a fault line, we understand, but in an underground mine, where I do much of the work that I enjoy, we really do not understand. The picture shown on the right side is a coal bump in a mine, underground, deep underground coal mine where the coal has exploded violently in a seismic event out into the openings. And I'll be talking more about this example in the next few slides. But the problem is we have an incomplete understanding of the mechanics prior to this seismic event. And so coal mines are one area that experience these unexpected seismic events, but additionally deep hard rock mines, and we will look at an example from a deep hard rock mine. They also have these seismic events that are unexpected or unforecast and challenging. And and perhaps some of those occur along a fault, but I suppose that perhaps some of them occur along inconsistent joints where you have solid rock that is under stress, and then due to excavation nearby, there is unloading. So we remove the normal fault force, and then there's a failure of this rock bridge. So there are these ideas about what leads to these events, but we really don't have a solid understanding. And so from the picture we saw before, as an example of the consequence of these events, one example is this Crandall Canyon disaster in an underground coal mine in Utah in 2007. And so the picture we have here is a horizontal cross section. So we have a north arrow. Each of these panels is perhaps 300 meters wide or so, and they have mined all of these out above and below. And this map shows the area where they were mining when this magnitude 3.9 event occurred. And this event occurred and resulted in the picture that we saw on the previous slide. And 6 miners were killed by that initial seismic event. And then subsequently, 3 rescuers were killed by later events. And so we really don't have an understanding precisely. Obviously, we did not forecast. This event was not forecast. I think in hindsight, we can say it was not a wise idea to be removing these pillars when there's so little support remaining. But but we can understand through numerical modeling some of what happened, and we'll look at some numerical modeling results, but it's leading to the point that even a small change in stress can trigger a very large seismic event. And so after this event occurred, there was some numerical modeling conducted, and this is the same area that we're looking at. And they Keith Heasley at West Virginia University did this numerical modeling, and they calibrated it with a previous coal bump. And then they looked at when they were mining around this little offset in the entry. And so we can see the stress distribution as they mine. So this is step 3 in the model, step 4, 5 in the model, step 6 and step 7. And we can see in between step 6 and step 7, the mining it mined these two pillars. And just removing those two pillars resulted in, as you can see, this massive change in the safety factor and the stability of the entire mine. And so these small, seemingly incremental extraction of these pillars resulted in this massive change in this large seismic event. And so we'll come back to that point shortly. But this was one example of why it's important to understand the mechanics prior to these seismic events. And so, as we said, this is the problem. We have an incomplete understanding of the mechanics. How can we engineer a safe design if we don't understand fundamentally what's happening? That's the challenge. And so what I propose, and others as well, of course, is to use passive seismic tomography to image the stress-induced velocity changes within a rock mass. And so sometimes I will, with these slides, I'll be talking about stress distribution, but of course we're looking at velocity distribution, and those two are correlated, as we'll see in a few minutes. And gradually, this is moving from art to science. We need this to be a standard tool that's available, just like many other tools, including point measurements and numerical modeling, geomechanical modeling. But we need it to be another tool that is available to help us understand the behavior of the rock mass. Now, one key word here is passive seismic tomography. There's active seismic tomography. We started with that, as I mentioned, at the Bureau of Mines. I was the source of the seismic energy with a large hammer. That was active seismic tomography. Then we moved to using the mining equipment itself, the longwall shearer, as the source of energy. But with this, we are using all of the mining-induced seismicity as the sources of energy. And so it's passive. We're just listening and using data that frequently is already available at these deep mines in terms of the monitored microseismicity. And so we can say, one of the things that attracted me to mining in the first place is the uncertainty of the rock mass. It's a natural material that's variable. And so we really have to be intelligent and reactive when we're working through it. Now, another natural material is the weather system. And so the meteorologists have this tool, Doppler radar, to see changes in the natural system that allow them to work to forecast what the weather is going to be. And so we want a similar tool for underground mining, a similar tool that will provide time-lapse indication of what the changes are within the natural system. Now, how does tomography work? The idea has been around for over 100 years. Radon theorized that the interior of a body could be imaged by analyzing energy that's transmitted from one boundary to another. It wasn't until the 1960s, though, that we had the computational power to take advantage of that. And so we had computed tomography that came on in the 1960s. And as we're all aware, it has grown in the medical industry, another natural system where we're looking at time-lapse changes within the human body. It has come on in the medical industry to allow great advances. And so we want to use that same ability in a rock mass. And so as a bit of background, if we have a field condition, maybe this is a pillar in an underground mine, perhaps. We have some sources here. This would be an active survey, not a passive one. We have some anomalous condition here. And we have these sources, and we have these geophones or receivers that pick up the seismic energy, and then we can invert to get a representative indication of the conditions of the real conditions. And so this would be the resulting tomogram. And as I tell the students, we are familiar with the term of pixels from cameras, and it's the same term here, except in a volume, we would call them voxels or volume elements instead of pixels or picture elements. But we have a representation, a pixelated representation of the actual field condition. Now, a couple things to keep in mind, and I realize these are just cartoons, and many of you are familiar with this method already. I hope they're not too elementary, but we need to be aware that if we only have access, here we have access on all four sides. But let's look at if we don't have access on all four sides, or if we have additional source and receiver locations, and the impact that that has on the resulting tomogram. And so here we have more sources and receivers, and that allows higher resolution. So a more detailed representation of the actual condition. So more sources and receivers, more crisscrossing ray paths, better results, more indicative of the actual condition. But on the other hand, if we only have ray paths that are subparallel, that aren't crisscrossing all over the place, as we did in the previous example, then the result will be more smeared. And so we'll have this smearing. And so we need to be aware of the angles of the ray paths when we use this method. So for best results, we want 360 degrees of coverage. We want ray paths that crisscross all different angles. That will give us the most reliable and correct results. And we want as many source and receiver locations, as many ray paths as possible. And again, this is in the medical field where we have the full 360-degree coverage. They are fortunate because they are using X-rays, which travel in a straight line, but we, of course, use seismic energy that refracts, and so that's more of a challenge. Nevertheless, the axiom is true that full 360-degree coverage gives better results, and many source and receiver locations give better results. Now, I mentioned that we want to understand the stress distribution within the rock mass, but we're actually monitoring the arrival times, and so it's the seismic velocity. And so how do those two relate? This is a simple example of a piece of a uniform sandstone with a steel platen, and then some ultrasonic, again, this is an active survey, ultrasonic transducers around the perimeter of it. And one by one, these would emit a signal and then receive a signal. And as we go up the stress strain curve, microfractures within the sample are closed, and then eventually near failure, they are reopened. And so we know that the P wave velocity corresponds to the Young's modulus. And so as the sample stiffens and those microfractures close, the velocity increases. And so here's a simple result that illustrates the change in stress observed through velocity and the correlation. It's not a perfect correlation. Nevertheless, there is a relationship. So we can use the velocity change to understand the stress change. So as I mentioned before, we'll be talking about passive seismic tomography. So we use the events that are recorded by a microseismic system to develop images of the rock mass. And we can do that to image stress redistribution and potentially fractured zones or zones where failure has occurred, where we have seen at the top of the stress strain curve that new fractures have been introduced. And that would be a lower velocity. So another example I showed earlier, one example from a coal mine. This is from a deep, narrow vein metal mine. And you can see the reference is shown there, but we have a few different views of this mine, kind of top down, a horizontal cross section, and then looking west. So northing is increasing and elevation. And then this would be looking north. You can see there are two parts of the mine. The red dots are the location of the geophones, and mining occurs in these two different sections. And these are plots of the induced seismicity over a full year in the two mine sections. And so the orange dots show the moment magnitude of individual events, and the blue dots show the the blue lines, the cumulative released energy. And so we can see that there are some significant events that occur, a few significant events that occur. And so graduate student Satara did an analysis before and after those to see if there were changes within the rock mass that could be observed. And the one that we'll be looking at is this one here. And so an important tool, as many of you know, is this for data quality, is this plot of distance versus travel time for the events. And these are two relatively clean plots that show a good distribution of arrival times. So our travel times, converted to arrival times converted to travel times, so that at zero distance, there's zero travel time. And we see generally a rock mass has a typical speed, seismic wave velocity, in this case of nearly 6,000 meters per second. And this is important to see the quality of the data. There are a number of mines I've worked with their data, and the quality is not good at all. They've moved geophones without logging them, but this is an important tool to understand the quality of the data before we move forward with the method. And so here we'll look at a series of results. So this is 5 days before the event. And the mining is occurring here where the red, each red dot, there are about 10 of them, is a blast at the mine face. And then the yellow dot is where the seismic event occurs at day 0. And so we're looking at two views here. One is kind of the end on, and the other one is a side view. It's the same data, the same result, and we'll look at this before the event occurs in the subsequent slides. But this is now, instead of a distribution of velocities using the rainbow spectrum, this is an isovelocity, so this is a high velocity zone. And we'll see how it changes, how it moves within the rock mass prior to the event occurring. So again, the event occurs here in this, we can see this white area that's a pillar, hard inclusion above some mined out areas and below other mined out areas. And that's where the stress is concentrated and where the event was located. And so again, we can see where the stress distribution is, the velocity indicating the stress, day 5. 4 days before, we see some stress starting to build near that hard inclusion, continuing to build 3 days before. 2 days before, it's more isolated, closer to that pillar, that inclusion, and again, 1 day before. And then they blasted for a production blast, and that is what triggered the event. And so it would be nice if we saw this. This was an encouraging result, but we don't always see this type of encouraging result. Ideally, it would be wonderful if we always saw this stress moving towards the area where the mining is occurring and concentrating, and then we could say, hey, you have a very highly stressed rock mass, you should give it some time to relax. But we don't always see this, right? I wish we did, but we don't always see this. We see just enough of these encouraging results to continue moving forward. But again, it's kind of like weather systems, and sometimes they behave one way and sometimes they behave another way. So it's very interesting, very challenging, but there are encouraging results like this. So the observations are that the event occurs after the rock mass very near to the mine opening becomes critically loaded, and it appears to be triggered by a mine production blast. And this ties back to what we discussed earlier, where in the underground coal mine, they had relatively small mining areas. These two pillars caused the massive change. And again, in this case, we say one more production blast, what difference does it make? But that, because it was a critically loaded portion of the rock mass, it triggered the large significant event. Thankfully, in this mine, there were no injuries. So again, as I've mentioned before, this proposed solution is to use this method to image stress-induced velocity changes within the rock mass. And we are gradually moving from an art to a science where it can be implemented by the mining operations. But there are a number of problems that we need to keep in mind as we move from art to science. One is the determination of the P-wave arrival time. We know there are many methods for doing this. Another one is the limited number of ray paths, and that limits the available resolution. As I mentioned before, we'll have the best resolution with many ray paths and many different angles of those ray paths. And then another one is that seismic rays refract. We have an unknown path of travel. And as you all know, I know you're very familiar with this. There are different methods, pseudo bending and fast marching, shortest path for approximating the seismic ray travel path. And those need to be looked at carefully and tested before they are accepted. And so I'll be talking specifically, I think, in the next few slides about this issue here, about increasing resolution in both time and space by, again, using template matching, a technique that many of you are familiar with. Traditionally, if you go way back, the arrival times for the P waves or S waves were picked manually. Now there are a number of different ways, there have been for a few decades, to pick them automatically. An example of that is the short-term average over long-term average ratio. But then another one that is used now is template matching. And so we'll talk about that and its application to improve passive seismic tomography. And so template matching is just, as many of you know, choosing a waveform from an event and then using cross-correlation to identify other similar waveforms that may be buried in noise. And so it can pick up the lower magnitude, lower amplitude events that traditionally would not be picked up either manually or with other automatic methods. And so it can add additional events to the database. So here's an example from another longwall coal mine. The data here were collected by personnel from the Spokane Research Center with NIOSH in the US. And these are just surface geophone arrays. We are looking in this area. The results that I'll show are using these kind of light blue surface geophones. And we have the velocity profile going down to a great depth on the right. But we'll look at an example using template matching from that portion of the mine. Now, with a coal mine, in a longwall coal mine, what we have, as we saw earlier, is this about 300-meter wide face, and they take about a 1-meter thick slice back and forth, back and forth, back and forth, all the way down this panel, and they allow the rock above to cave. And so we have this gob or goaf zone behind it. So this has less support. There's more support here. And so it's an excellent laboratory for understanding stress distribution. Frequently, we look at rock stress either on the core samples or at the crustal scale. But an underground mine can be an excellent lab for at kind of the 1 kilometer scale for understanding stress redistribution. We know exactly where the face is day by day, and we know that we should expect a high stress forward abutment that moves just ahead of the face, and maybe some side abutments on the pillars on either side of the gob. And so we have this target that we expect to see. And so it's a very good lab. And so this shows some of the data that were used for template matching. In the blue, we have the number of events day by day, but then using the template matching, the results are shown in red. You can see that we have more than double the number of events made available through using that method. And so we can have higher resolution results. So using those results, then all the additional travel times through the template matching, we did the tomograms. These plots again show the additional the additional events that were obtained. In black were the original events, and then subsequent days in red show the event locations using the template matching. I think the ones over on the left are incorrect. They were the bounds of the box that the graduate student was using, and so we did not use those. But then again, as we saw before, plotting the distance versus the time, the travel time. In this case, we have a lower velocity. No, it's still about the same, still about 6,000 meters per second. And we see a number coming in much slower, much later. And this is not there. It's either bad data or not unexpected because of that caved zone behind the face. These could be arrivals that are refracting around that caved zone, that gob, and coming in later. So again, though, the data quality is not bad. And this is what we saw then, kind of day by day. In this case, we've reoriented the plots, and the face is moving left to right and gradually over time moving down towards the bottom. And we have the silver cylinders that show the surface geophone locations. And I'm not very happy with these results. They're not as consistent as I would like. Sometimes we see this low velocity zone, and others with the same data set have seen this low velocity zone, and it's a head scratcher. We don't know why it's there. But the big takeaway is that we see the forward abutment stress, this high velocity zone, moving down through the panel day by day, just as we would expect. And so it's kind of a proof of concept that we can use template matching to increase the number of events that are available, number of ray paths that are available, so that we can look with a higher resolution, both in terms of pixel size, but also in terms of time. We can look at a shorter time frame and still have enough data to construct a tomogram with low uncertainty. So that's one method that's available and needs to be included as we move forward using this methodology. So the observations from this data set, we have progression of the forward abutment, kind of an unclear development of the gob or the goaf behind the face. I'd say the results are geologically reasonable and correlated to expected conditions. And as I said, this method allows more events to be used so that we can have higher resolution in time and space. Now, another thing, another problem, another opportunity is to quantify the uncertainty of the tomograms. And so we can use synthetic calculations for this, as many of you are aware. And the classic way to do this over the last decade or more is with the checkerboard test. But we can develop a synthetic velocity distribution. We can calculate, the velocity distribution would be a checkerboard or a spike test. We can then calculate synthetic travel times propagating through that velocity distribution, conduct the tomography, and compare those results to the initial synthetic velocity distribution. It would look something like this, where we have a checkerboard velocity distribution with some real event locations. We can cut down to one cross section, one elevation where we have good data, and we can compare the high velocity observed with the low velocity distribution that we expected from the checkerboard. Yeah, I guess this is another example of that in the event locations. And that's fine, but I've wondered if maybe it's too arbitrary of a velocity distribution. So this one is, I'm remembering now, this is not the standard checkerboard, this is more of the spike, where we have the gradually kind of sinusoidal variation of the velocity and not the hard abrupt contrast of the checkerboard. But I'm wondering if this is maybe too arbitrary and misrepresents the expected ray paths in the field. And so I have a paper due on Monday to Savka for the rock burst and seismicity, induced seismicity conference that will be held in August. And I'm afraid, Savka, I may be a day or two late with the paper. It's coming together, but I apologize for that. But I'm kind of proposing in the concept, the idea, perhaps instead of using, so I'm going to camp on this slide for 1 or 2 minutes. It's an idea and it's a concept. Instead of using this arbitrary checkerboard or spike, maybe we could use the velocity distribution that's expected at a mine through geomechanical modeling, through numerical modeling. It's frequently used, finite element, distinct element, boundary element, especially finite element, distinct element, to give the volumetric distribution of stresses within the rock mass. The issue, though, with these models is that they are uncalibrated, and we can calibrate them with a variety of geotechnical instruments, but measurements, but those are usually at certain points, and the model itself is volumetric. And so it needs to be volumetrically calibrated. And so what I'm proposing is to use the tomogram in combination with a geomechanical model to do a coupled validation of both. So we would do a geomechanical model, instead use that as the velocity distribution instead of the checkerboard or the spike. And so we would use the stress distribution from the geomechanical model and identify areas of high stress and maybe fractured low velocity. And then we would use that as the synthetic model and calculate our synthetic travel times and then get an assumed tomogram. We would have the actual tomogram from the actual data in the field, but it has areas where it's uncertain due to poor ray path coverage. And just like with the checkerboard or spike test, we identify those. We have areas of uncertainty. And so we can combine all of these then to say, based on this model, we know where we have low uncertainty in the tomogram. So just as we do with the checkerboard or the spike, we can say we have low uncertainty in these areas where we have very good ray path coverage. So we can identify areas of low uncertainty, and that helps us interpret the tomogram. But additionally, it can help us to calibrate the numerical model because we could say we have low uncertainty in some areas, and interesting, we're seeing something that was not included in the geomechanical model. And so we can use that then to improve the geomechanical model and have a more calibrated geomechanical model and a more certain tomogram. So instead of using the checkerboard or the spike, I'm considering the possibility of using the velocity distribution from the geomechanical model. So that's another thing that we can use to improve the tool as we move from art to science. And so to kind of summarize, we cannot design a structure until we fully understand its behavior. And this tool is just another tool, passive seismic tomography. It's an important method that we can use to understand the rock mass behavior and then design something that is safer. And we now have tools that will help this method to provide quantitative analysis of the rock mass behavior. We can use template matching for more robust arrival time determination. We can also use it for additional event locations and ray paths to increase the resolution in time and space. And then we can quantify the uncertainty using geomechanical modeling. And all of these need to be done to provide kind of the best practice and the most reliable results with the tomography so that the results can be trusted and can be helpful. As we continue to study examples, we'll develop improved understanding of rock mass behavior prior to these seismic events. So I appreciate the opportunity to speak today. And Alex, if there's time, I'd be happy to do my best to answer any questions.
Thank you very much, Eric, for this nice presentation. I will stop now the recording.